Percent composition is particularly useful whenever we look at something called combustion analysis. So one of the things that we do in science is when we don't understand something, what we tend to do is we tend to break it up, burn it, destroy it, convert it to something else, slam it together into something, and see what pieces fall out. And that's what we do when we're talking about combustion analysis. Basically what we do is we take some sort of sample and we burn it. And whenever we burn it down as far as we can, and then this vapor right here goes through these tubes. And the tubes actually consist of two different parts. There's a part that absorbs water, and you can find the mass of this before and the mass of it after. And whatever the change in mass is lets you know how much water was produced by the reaction. And then you have something that's called the carbon dioxide absorber. And it does the same thing. The carbon dioxide comes through, is trapped. You can find the change in mass that's there, and you can figure out the carbon dioxide that's present. So using these two things, this carbon dioxide and this water, you can turn around and figure out exactly what it was that you burned. It's something called combustion analysis, and it's one of the biggest tools that people have whenever we're trying to figure out what certain compounds are, especially hydrocarbons, which are things like gasoline or natural gas or something along those lines. So, combustion analysis requires that you have this formula C6.6.2, and what you do is it's somehow converted into a combination of carbon dioxide and water. So what you can do is you can use the percent composition, you can use these formulas, how much carbon, how much oxygen, how much hydrogen are present that you figured out from here, and you can go back and retroactively determine what these numbers are. It could be something like C2, H10O1, it could be. Or it could be any number of a number of other things. So the question is how do you go from percent composition to the formula that it actually was? And here's what you do. Number one, you convert all the percentages to mass and you assume there's a 100-gram sample. So in other words, 31.17% becomes 31.17 grams of carbon. 6.49% becomes 6.49 grams of hydrogen. You're just taking the percent sign and you're replacing it with a gram sign. You also have to make sure that the element that goes with it is there as well. So once you've done that, now you need to figure out the number of moles that are present in your sample. So you take the gram formula mass. Okay, so it's another one of those things where you look at the periodic table, you find carbon, you see carbon is 12, and when you see carbon is 12, or hydrogen is 1, or oxygen is 16, then you can use that gram formula mass to figure out the number of moles. Now, generally speaking, you do not have to take it out to 12.011 or 1.00794 for hydrogen. You can just leave it as it is at 12 or 1 or 16. Everything else will kind of work its way out, as you'll see in just a second. So, if I had a 100-gram sample like we talked about before, that would contain 2.5975 moles of carbon, 6.49 moles of hydrogen, 3.89625 moles of oxygen. And to tell you the truth, that doesn't really make a whole lot of sense. It doesn't actually give us any useful information. So what we need to do is we need to say, okay, it's clearly not this. The reason why is you can't have a part of a molecule. It has to be carbon 2 or it has to be carbon 3. It cannot be carbon 2.59725 because you can't cut a carbon into that many pieces, or any pieces at all for that matter. So what we do is we find the lowest number of moles. Okay, if you look, the lowest number of moles that we had before, was 2.5975. So I take all the values and I divide it by 2.5975, and as a result, what I get is 1 carbon, I get roughly 2.5 hydrogens, and I get roughly 1.5 oxygens. So that right there is getting close to an empirical formula. But I still have this problem. It's still not going to be C H 2.5 O 1.5. So now what I need to do is I need to multiply all the numbers by the smallest value that will result in whole numbers. And if you look, this 2.4985 is roughly 2.85. Remember, we didn't use the exact gram formula mass. This oxygen is roughly 1.5. So when you multiply it out, you get 2, 5, and 3. So then the formula for whatever it was based on that percent composition is C2H5O3, and it's finally done. Now this is one of those procedures that takes a little bit of time, and you need to be able to say, yeah, it's at 1.5. Is it close enough to 1.5 to count it as 1.5, or do I need to do something else with it? That's one of those things that it takes some practice. You need to make sure that you do some things with this. But now we have a problem. Based on this particular formula, I got C2H5O3, but I was originally told that the compound was C4H10O6. So I've got a discrepancy here. Okay? If you look, these are two clearly different compounds. One has 4 carbons, one has 2, one has 10 hydrogens, one has 5, one has 6 oxygens, one has 3. But if you were to take a look at these, they have the same percent composition. Okay, they represent the same percentage of the molecules. And that's one of the biggest problems with percent composition is it can just tell you the ratio between the atoms. It can say that for every 5 hydrogens, there are 2 carbons. It doesn't let you know necessarily that there are 10 hydrogens and 4 carbons, or 15 hydrogens and 6 carbons, and so on and so on and so on. So you need an additional information if you want to figure out what it actually is. Now this right here, the lowest common denominator thing, is called the empirical formula. The empirical formula is the simplest whole number ratio of atoms in a molecule. For example, if you took a look at this is what I originally had. That's not the simplest combination of atoms. I could take all of those and divide by 2 and get C2H5O3. That right there represents the simplest combination, because if I were to divide by 2, I would get CH2.5O 1.5, and you can't have half of an atom. So because of that, this right here is what we call the empirical formula. And the percent composition, whenever we do those calculations, can only tell you the empirical formula. It cannot tell you the molecular formula. So because of that, you need to be careful about what you say as a result of your percent composition equations. So, working backwards, combustion is just one type of reaction. There's lots of other ones that you can do in terms of percent composition, but regardless, if you're given the percent composition, you use the exact same process that we used with combustion. Okay, if you have any sort of percent composition data, you should be able to derive the empirical formula from that percent composition. Now let's look at a couple of examples. The first one says a sample is combusted in the data shown below. You have 40% carbon, you have 6.67% hydrogen, and you have 53.3% oxygen. So we need to go ahead and figure out what the empirical formula is based on that. Now eventually we want to get the molecular formula, but we'll talk about that in just a minute. So the first thing that we need to do is realize that these are not percentages. These are grams. Okay? Then what we would do is we would divide each by the molecular formula, or the molecular mass of each element. So carbon is 12, hydrogen is 1, and oxygen is 16. As a result of that, we will get the number of moles of each in the sample. So for this first one, we have 3.33 moles of carbon. We have 6.67 moles of hydrogen, and we have 3.33 moles of oxygen. So we have C 3.33, H 6.67, and O 3.33. Now what we need to do is we need to divide by the smallest number that's there. The smallest number is 3.33. So we divide all these numbers by 3.33. And as a result, we get carbon, there's 1, hydrogen, there's 2, and oxygen, there's 1. Now remember, what that represents is that represents the empirical formula. But remember, I'm trying to solve for the molecular formula. In order to do that, I need another piece of information. I need it from somewhere. So there's lots of other places the information can come from. You can be given another data set, another test, something indicating how many carbons there are. And in fact, in this case, it says further analysis shows the sample to have 6 carbons. Well, if there are 6 carbons, you need to multiply carbon times 6. But you need to do that for each molecule, or excuse me, each atom in the molecule. So as a result, this is actually C6H12O6, which you learned about in biology as glucose. Next, it says a student is attempting to ascertain the identity of a sample based on the information below. It says you have sodium, that's 32.17%, hydrogen, which is 1.4, phosphorus, which is 21.68, and oxygen, which is 44.75. So remember, the procedure is to say that these are all grams now, not percent, and to divide them by the molecular mass. So I would go to my periodic table, and I would make sure I knew what the molecular mass for sodium is. Remember, sodium's element 11, and it says 22.989, which is roughly 23. So we'll say divided by 23. Hydrogen is 1, phosphorus is 31, and oxygen is 16. When you divide that out, you end up with 1.4 moles of sodium. You end up with 1.4 moles of hydrogen. You end up with 0.7 moles of phosphorus, and you end up with 2.80 moles of oxygen. So you identify the smallest number, which is phosphorus. You divide each one by 0.7, and when you do, you end up with 2 sodiums, 2 hydrogens, 1 phosphorus, and 4 oxygens. So that is our molecule, Na2H2PO4. The last example that we have, very similar again, says what is necessary to have a combustion reaction and what does it produce? One of the things that you need to know is that a combustion reaction is generally taking something like C6H12O, where X, Y, and Z can be any numbers, including 0. So for example, you can combust something like CH4. Even though there's no oxygen, the Z value is just 0. You can combust something like H2O, okay, because you have just the C or the X value is 0. But in this particular case, you have to have something like that, and you have to have oxygen present. Okay, that's the requirement. If there's no oxygen, something will not burn. You can actually make a fire, you can control the temperature of a fire by increasing the oxygen flow or decreasing the oxygen flow. And in this particular case, the more oxygen you put in, the more it will burn. Okay, as a result of mixing these two things, you will produce some combination of carbon dioxide and water. Now, the carbon here must come from the carbon there. The hydrogen here must come from the hydrogen here. Now the oxygen's a little bit different because the oxygen can come from either the molecule or what it's burning. So that's where it gets a little bit trickier in terms of trying to balance out the equation, which we will talk about in the next unit.